battery out. Okay. So the way this thing works is it's got an emitter surface, which is these individual top thin filaments that look like wires. It's got they're actually filaments, and they have emitter wires glued to them. And the emitter wires are on this vehicle are 2.8 microns in diameter. 2.8 micron diameter wires, so they look like a tungsten cobweb, basically. And they glue them along the side here. And tungsten doesn't react with air as long as you don't heat it up too much. So they last for quite a while. Recently I replaced these filaments with high-tech stuff that doesn't stretch, and that stopped them from breaking. And then, so now they're more reliable. And then this collector surface here is made of silver-coated polypropylene, which is very light, low-density plastic. And the silver doesn't oxidize too fast. You know? Whereas this old one here, this one's a couple years old, and it stays in perfect shape, you know. But it's got a real thin oxide on it, because this one's aluminum, you know, aluminum coated. It's just a couple hundred angstroms, or 100 angstroms thick of aluminum. So if I test it with my voltmeter, you know, test continuity, it doesn't beep. You know, it's no longer conductive. But this one is conductive everywhere. You know, and it's still good. So the way it works is that the battery's plugged in on top, and that's plug here, and then these are these batteries are 4.2 volts each, lithium polymers. And since there's 4 of them, 2S, 2P, 2 series, 2 parallel, they put out 8.4 volts total in series. So that 8.4 volts goes in here, and it goes into a buck converter, which is a step down, regulator, and it puts out 4.5 volts to run the receiver, which is a little 125 milligram chip here. So there's buck converter, and then that's for the receiver, right? And then the receiver goes to a little MOSFET driver chip, because the receiver doesn't have enough power to run this. There's a stack of 10 MOSFETs here. They're very tiny, like, you know, mosquito-sized MOSFETs. So they have a tremendous power to weight ratio. And I have this is a pyrolytic graphite that conducts the heat along them, so they all share heat evenly. So that's how it's throttled through the receiver. The transmitter's over there, right? There's 8 old ionocrasts here piled up in the back here. Actually, some of them look a lot better than that if I took them straight in the eye, they look pretty good. Those carbon ones don't work because of the texture of them, just causes problems. But there's 2 more ionocrasts in the other shop there. And that's my vacuum chamber. That's a 30-inch vacuum chamber. I pumped it down near the like space almost before, and the bottom plate there, it was bending up into it. It's pretty dangerous. So okay, back to this. The battery plugs in on top, goes through the regulator, through the receiver, through the MOSFET driver, through the MOSFET stack, which is, carefully, it took a while to design it, so it's so light and powerful. And then that goes through this. There's a Royer circuit here, which is it's a resonant Royer circuit, which drives the transformer. And there are 2 stacks of 10, I think 8 or 10 very tiny transistors that drive the transformer. And they're very specially chosen, and they also have pyrolytic graphite, so that one of them doesn't get hot all of a sudden, overheat, and then that's what all these little wings are. They're just graphite sheets. They're like heat sinks, but they have no mass, So this little disc here is a transformer made of special ferrite. And as it turns out, the higher the frequency of the transformer, the smaller of a transformer you can make. It's not an absolute rule, but each ferrite has, and shape and size of ferrite has an ideal frequency that it works at. So as this transformer here can do what a much larger transformer normally would do. And so, if you just look online and order a transformer, it's going to be something big and heavy. It's not going to be developed like that one was. So this has got special very special wires, and it's got it's called the Q. It's got 4 coatings of enamel on the secondary, and when this transformer resonates it just right, it stays in a thing called strike mode, which used to be used to start fluorescent lamps, and that one can go up to 4,000 or 5,000 volts, and but at that voltage the current is a little bit lower, but the max current is about 1 milliamp on that. So it's not a lot of power, but this thing doesn't need a lot of power. And by having such thin emitter wire and this big wide gap here between the two surfaces, it creates a lot of resistance. And with that high resistance, it just doesn't draw a lot of power. And then the stalk here is a voltage multiplier. It's a hybrid between a standard Takeoff ball and half-wave reverse voltage multiplier and this one that I invented, where it's an elongated voltage multiplier. It goes all the way from the top to the bottom, and that gets around having to have you could have a smaller one, but you have to have a whole bunch of insulation and then a wire coming out of the end. And if you look at that under the right kind of camera, you can see a whole bunch of corona building up on those stubby voltage multipliers. So this one saves a lot of power. So and then these two things here, they're little tiny servos on each side for steering, the steering system. There's a servo here and a servo here, and it moves these two little arms back and forth like that. And those little arms touch 2 little springs here. See these springs? I call them whisker springs. And those springs are directly connected to the 4 quadrants. The outer ring is a steering ring. Okay? And it's segmented into 4 pieces. You see where this thing is here? I call it a steering box, but it's just a place where the emitter wire can go along and curve up, and then terminates up higher here. If I terminated it right, normal height, it would spray off a bunch of ions, that build up corona. So it helps to have it terminate at a higher point, at the top of the steering box, so to speak. And then the wire that comes from this whisker spring goes along here above the vehicle to one of the quadrants. You see the outer ring is segmented into 4 pieces, I think I mentioned. So if you shut off the power to one of the quadrants, right, it's going to lead in that direction, right? Or if you want to stabilize it, say it's starting to do this, you shut the power off real quick to the high side, right? But normally they're all on. So if I just put pods around the side or something, that would weaken the structure. This is a better arrangement. And if I feel that it needs more steering authority, I can make it a larger outer ring. This outer ring is 3.5 inches out, I call it. If you notice, all the rings are 3 inches apart, and the outer ring is spaced more. For that reason, it gives it more twist, So, okay, now I'm gonna turn my back to the camera here and plug in this battery. They're very powerful little batteries, and they're kind of a bit dangerous. So, all right, here we go. Oh, and I better turn the transmitter on first. I don't know if anybody wants to. I guess everybody's taking videos, or some people are, so you don't really need to have a separate ultra high definition camera. So I'll just, I put the transmitter on. Goes, how she works. I'll come over here because this is a spot to plug it in at. There's some danger to me to do this, but normally I do this from a round glass table, and but I've done it on the floor here because I wanted to make like a little runway where I could fly without tie downs, but can't say it's necessarily ready to do that yet. Make sure it's plugged in right. There. Okay, it should be activated. Watch this, see if those little switches go. See? Yeah. backward. Okay. Okay, so now I'm gonna go ahead and energize it. It has to warm up for a few shots first. Maybe several. It's sticking on too. That's not. It's not getting. It's not conducting 100%. Starting to lay the ground.
Mm-hmm.
I have two more battery packs to try if this fails. God forbid. Here it goes. That's embarrassing. It really kicks in good when it goes, but it's.
Maybe you should check whether it's stuck to the floor.
No, it's not. It's not kicking in like it should. It could be the battery might not be plugged in well enough. Let's try it. Two more batteries to packs to try. So, figure it out. Just flew this morning. So we let a bunch. Oh, you know what? We let cold air in, and I was going to heat the batteries up on this heater before flying it. Don't get too close in case that's an issue. But it shouldn't be that cold. It's not that cold in here.
Should we all come in and close the door?
Well, let's see. You can see it started to take off.
Yeah.
But it didn't quite yet. So let me try it. Let me see how many volts are in this battery pack. Do this quick while it's voltages. Maybe it wasn't charged all the way. The battery couldn't. Test it.
How sensitive is it to
7.6.
How sensitive is it to minor variations in charge?
When it's running properly, I take off on 40 to 60% throttle. Let me put this on here just for a second. That battery not charge it. And usually I remember to test the voltage first. So yeah, it usually takes off on 40 to 60% charge after it warms up just for a second. And then it will run, and then it starts getting weaker after like a minute, and I increase the throttle a little bit, and then after just under 2 minutes, it's pretty much depleted.
And that warm-up time is that just to build up that layer of ionized gas around the?
No, it's the emitter wires put out a little bit more ions when they're warm, and everything sort of balances out better the way it powers up. And the batteries, when the batteries warm up, they have much lower internal resistance. Warm batteries, if your cell phone ever dies, you can take the battery out and warm it up a little and start it back up. So, well, I think the new cell phones, you can't take the battery out. But it used to be. So,
And what are these? Are these like little,
those
big,
posts?
Yeah, the posts.
They're made of very high-tech plastic and very light tubing. They're tubing.
Okay.
And
what's the rigid frame? I noticed these little black wires.
Yeah,
that seem to be
those black wires are boron filaments. They're like harder and lighter than carbon fiber. And I wanted to mention before I started all this, I'm sure the camera shut off. She's got her stuff. I wanted to mention before I start all this that the vehicle works by adding electrons to the oxygen molecules. Oxygen grabs up electrons, that's why it's called an oxidizer. And so it likes to gain a few electrons in the outer orbital shells, from what I read. I mean, you can't see it, so you just see it fly, But so it gains a little bit of negative charge naturally, and so all it needs is an electron source, and that very thin wire produces a high pressure, small high pressure source, but it's not ionizing a lot of the oxygen, and it doesn't have to reach the ionization potential. There's like an energy level that a certain amount of wattage you have to put in to like strip electrons loose from xenon, for example. You don't need to reach that to just add some electrons to ozone. So that's very efficient. But I would like you guys to see it take off. That would be very, it's gonna take off today. Okay, let's try it again.
But it's not a super rigid frame. It's sort of like almost like it almost looks like an inverted umbrella with these filaments that then lift up the central.
Yeah, well, it has 45, not quite 45 degree, but it has filaments that go from that little lasso point there down to H point.
Okay.
Filaments. So these are almost like a noodle, if they didn't have a whole bunch of guy wires, guy threads.
Okay.
And the bottom, see the bottom there?
Just keep the that central post upright.
Yeah, it keeps the post upright and it keeps this from collapsing, right? Underneath, it's got the same thing. When it starts producing lift, it would bow upwards, you see?
Oh, okay.
So it's got a whole bunch of filaments going down to those two lasso points. You see the two white lasso points underneath?
And that's how you can convey the lift to the central.
Yeah, to the central portion. But this was a modification. You see how it's got one lasso point and then another one underneath? It was starting to bend when I put steering on it and everything. So I thought, well, if I put these support filaments going to a lower point, they pull in less on the spoke-like members. You know what I mean? The further down that under post is, the easier it is on the spokes. So that adding that lower point down there strengthened it and made it work. Now the next version of this, I'm not going to have that higher tie point. I'm just going to have it at the bottom, and that'll save several hundred milligrams there. Let's get this sucker flying. That's what we need. Okay, it's plugged in.
The legs are leaving the ground.
Also, I'm going to put better legs on them. I extended the legs, that's another modification. It's very tough in that form, but when you start making the legs longer, I had to make the legs longer because I made the post longer, and that created some flimsiness. It started to leave the ground, the center left the ground, but it didn't do what I wanted.
There's like a, oh, there we go.
What exactly are the noises it's making?
Some of it is, to be quite frank, electrical arcing, which shouldn't be there. Some of it is, it's very high frequency electrostatic energy production in the inverter circuit, and kind of hear the lower undertones from it, and the air moving, and ions. I have one more battery pack after this. And then,
It's definitely left the ground.
it's left the ground, but it was not real impressive yet.
Yeah.
Which is, but there's 35 videos of it. You can see varying. Some of them it kind of floats up just barely, and some of them just like falls upwards.
Yeah.
So it did sort of leave the ground, but I don't consider that. That's not what I'd like to see yet.
So right now it's not just leaving the ground goal because that happened in 2006, right? So right now it's with steering.
Yeah, the one in 2006 was hanging from a postal scale, and it was incredibly flimsy, like almost nothing to it, and it would just hot for a second, and the transformer burned out. And I thought, oh my God, it can be done, And so I started working on it. It would fly longer and longer, and don't know what happened with that little bit of lift. started to leave the ground, but not yet. Let's try.
The motion dominated by a force other than gravity. At least at least it's motion dominated by a force other than gravity.
Yeah, I mean it did. Well, kind of broke gravity. I mean, but I think one or two legs were dragging a little bit.
Yeah.
You know, but this is not what I wanted to show you guys, but it's better than nothing.
Yeah.
Thank you for showing.
Oh, you gotta go.
I gotta go.
Thank you for stopping by. I'm sorry it
No worries.
wasn't at its best. Let me try again. We got one more to try. And it did do better on the second try, even though the batteries were older. There's 8.42. No, well, yeah. Could be a good sign. Okay. Let's give it another shot.
No, I thought it actually could be.
Things come to those who wait, I guess. Okay. Silver prayers. It doesn't want to shut off right now.
Oh gosh.
It could be. It could be sticking on, these tie downs are sticking on the material. Ah, a little shot. Okay, almost, I would say it's down to like one leg still touching.
It's like the
One can definitely feel under
Oh yeah,
it
it's
some-
blowing, yeah.
Yeah.
Sure.
Oh yeah.
You can get a little shock from it, so I would.
Yeah.
It won't be it's not
Right, with
that
the-
dangerous. It's like touching a doorknob, but
yeah.
also if you put your finger on it, it will, and then you look at the place later on this silver coated material, you'll see a fingerprint appear after a while, and it creates a power loss. So you can see the steering. Well,
Is it like interfering with its radio signal?
no, because the transformer runs it varies. It depends on the transformer and the load, but something like 360 kilohertz, and this is 900 megahertz. So it should have just jumped in the air like crazy. I'm sorry, you guys, it barely flies, but it did. I would.
What's causing it to? I notice sometimes when you move the stick down, it doesn't shut off, which causes.
Yeah. Sometimes when there's an open circuit on it, it doesn't have enough load to operate properly, and the MOSFETs that are the throttle part to drive it have a capacitive, they work by capacitance to some extent. And so if they charge up and then that capacitance doesn't drain out of the MOSFET, it'll just stay conducting. So that's, it's like there's several theories, and I can't tell you absolutely for sure how much each one, contributes. But I know, I can tell you, like for instance, if it runs and the batteries get real hot and they run out in a few seconds, I know I probably have an emitter wire hanging down. If it runs like for a really long time, doesn't draw any energy, and sticks on a lot, I know that it might not be hooked up right, bad connection. So it's not hooked up right. That's the thing. Maybe it's the plug was dirty. A little bit of dirt on the plug. Anyway, you feel any wind? It blows quite a bit. But it's not like a quadcopter. It's, I really wanted to see it more than that, but this is the physics.
Sometimes this is the way of sometimes it goes, and then sometimes it goes into the ground.
I mean, you see rockets, but $1 billion blows up, and no great loss. This is old. This one's been through so many changes. I've put it had like a bunch of V-shaped part, extra pieces for steering, and then, at one point it had 11 rings. This has been through like a dozen changes, so it's time to rebuild. I made this, let me show you another thing. This is a carbon tube here. It's 0.3 by 0.7 millimeters. And, but the thing with it's much more rigid than that boron because it's in the form of a tube. It's not a solid rod. So, but the thing is it weighs like 460 milligrams. And I really need to get it down to about like 200 because by the time I expose the whole thing, the weight would be a little high. So if I stand on the outside of it, it will lose more than a linear amount of rigidity because the rigidity of a tube is somewhat proportional to the square of the diameter. Might be cube, but I think it's closer to the square. It depends on some other factors too, but the point is that it would be better to enlarge the inner diameter rather than shrink the outer diameter to take some weight off. So I thought, well, gee, wouldn't that be cool if you could just drill out this tube? But nobody has a drill bit that would do that, You can't do it with a laser, it would ruin it, So, plus somebody would charge a lot of money to try. So, but I thought, hey, you know what? There's this wire that you can get, this very thin, this wire, that is coated with diamond dust. It's used for sawing through steel, right?
Yeah.
And so if I make So if I make a device that pulls this wire real tight and spins it real fast, right? And then I make a fixture to hold this rigid, then I can cut away the inside and enlarge that inner diameter with sufficient accuracy. It might be perfectly accurate, but it'll be decent. So I made this fixture. Yeah, that's what this fixture is. And it's got two little drill mandrels here. Careful of the machine over there. It's got these two little drill mandrels and this motor, and it spins those. This wire is going to go in these mandrels. Right? And then I'm going to put this into this, piece of iron angle aluminum, right? And then I'm going to put little bits of this aluminum tubing to hold it in this corner. And I have a thing called a cross-slide vise. Do you guys know what that is? You know what a vise is, right?
Yeah.
So it's like a vise, but you turn a crank and it moves it back and forth within thousands
Oh,
of
okay,
inches.
yeah.
Yeah. So it's kind of like a part of a lathe, So I'm going to clamp this in there, and then this is going to be spinning. It's going to be fixed, this wire, and then I'm going to crank it, half a thousand, take off some, and turn it, and strip that out so I can get it down to 200 milligrams, and then I can rebuild this thing, and it'll be like 3 times as rigid,
Wow.
So and then just one of the things plus the bottom will be fixed, and there's a whole. And I'm going to use. I got 2.2 micron wire. This one I bumped it up to 2.8 micron emitter wire because I thought it would be last longer. But then I found out the reason it was breaking is because of the stretchy support filament, the horizontal support filament. So the 2.2 will be fine and get much more efficiency. So that's kind of what's going on in this shed.
Cool.
I'm going to do some vacuum tests later. I have videos of this thing flying, of these old 8-ring models, flying. You actually have them with some steering system also, flying with carrying propellant tanks. They didn't have anything in them. But thank you for stopping by.
Thank you so much.
So yeah, it's carrying propellant tanks. So I'm going to make a smaller one, put it in the vacuum chamber with a propellant tank.
My propellant tank is just like a little weight, or?
They're little tiny tanks. Have you ever seen CO2 cartridges? They're like
to try and just have some gas you can release that'll then so that the only force is going over that.
Yes.
Okay.
It'll release. I'll have some little tubes with little irrigation hole like things, and it's going to blow down over the top of it, and then it'll work in the vacuum chamber. And this is very efficient this way, charging oxygen that way.
Or do you get the pure oxygen rather than all the other junky and
and they'll sell it really fast because there's nothing in the way, And like I said, it only uses a tiny percentage of the oxygen in the air. These have been tested, similar devices in oxygen environments, pure oxygen, and it had just hardly any extra lift, which implies that it really is only using a little of the oxygen, right? And then and the nitrogen had almost no lift.
What's the bottleneck on the thrust that this produces?
The bottleneck, there's a bunch of weird physics to it.
Yes.
The thing is that once you start, using small amounts of air motion, slow moving air to propel something, it becomes really efficient.
Okay.
Have you ever seen a human-powered helicopter?
I have not actually.
There's a helicopter that's powered by pedaling, and it actually works.
Mm-hmm.
But in order to make it work, they had to make this huge propellers that move very slowly, And they got a really strong guy, and the guy won a prize for pedaling it for a whole minute,
Oh, jeez.
And he went up, and at one point he went up 11 feet high. I forget how many meters that is.
That's certainly more meters than I would be entirely willing to trust my
Yeah,
own powers.
when he was testing it, it broke a couple times. He fell. But that illustrates what I'm talking about. With a low power source, you can lift a lot of weight if you spread it out. If you spread the air motion over a large area. When you move air fast over a small area, it becomes very inefficient. Yeah, because it's moving the turbulence. Yeah. So
I was supposed to want like that laminar flow.
yeah, it's like a snowshoe. If you're on the snow, you know what a snowshoe is?
Yeah.
Yeah, if it's too small, it's going to take a heck of a lot of energy to stay on the snow. But if the right size, it'd be very easy to.
But you're like using, you said, a very small amount of oxygen in the air.
Yeah.
Which I guess, does that like move more air, I guess, then?
Well, if you move, it's a small percentage of the oxygen. I mean, there's something to be said for the theory that's well known that it creates particle collisions, and that because there's nitrogen, and most of the oxygen that's uncharged gets propelled along with that small amount of charged oxygen. And so a lot of what comes out of the bottom is uncharged, but a lot of it is actually charged also, which isn't in the literature. I had one in the garage that was like 6 feet round. In fact, I might even have a picture of it right here, but I'm not sure of that. Maybe not. Okay, maybe not.
I think it's on your site.
Yeah. Oh, it's on my site. Yeah.
Are you
But
just doing this yourself? Or, I mean, I noticed there's this.
oh, electron here.
Yeah.
Yeah.
Is that just you?
It's just me. I thought, what would be a cool name for a company? Like 2000, And I thought, how about Electron Air LLC or Electron Air Inc. And then I used to live at a different address. And I got some help from the legal program, pro bono program on a case, and I got 2 patents now for this thing.
Oh, wow.
And for free. I just had to pay a patent office. And so because people thought it was impossible with a power supply. There's no way. I mean, you know how far away a normal ion thruster is from lifting a power supply? It's like no way,
And and I guess the reason you don't have the reason it's loose and you're just basically holding all of that stuff up with the rigidity of just the wires, just because a board would be too heavy.
Oh yeah, circuit boards tend to be too heavy. They're just extra dead weight,
Okay.
So I have made all kinds of circuit boards using this flex circuit material, and I got some that's like 12 microns thick, and that works pretty well, but it's not very. It's still not so great for a prototype, and then you gotta etch it and all that.
So I guess your limit is that you've got only a certain amount of force per square meter that you can uplift that you're producing.
Well, I could produce considerably more force per square meter, but the efficiency just takes a dive like.
So
terrible.
any given efficiency.
Your limit is really the power, right?
The limit is it's not really power. You see, everybody thinks you can use raw power, just up the amp, up more amps, more watts,
Yeah.
And what happens is they just can't do it with the kind of transformer that they need and the kind of batteries that they need.
Okay, so you're using an AC. So you're using AC to drive the propulsion.
No, the AC it's AC that comes out of the inverter, and that goes into that long voltage multiplier,
Okay.
and that comes out high voltage DC.
Okay.
Yeah.
So this thing that's producing your lift is DC driven.
DC, yeah, very high voltage, very low current DC. So it's not really much power. Well, this one's not running very efficiently right now, but it used to be. It's just this. I was using 2 of these little batteries. And they would run for like 45 seconds. And now when you take off with them, I have to use 4.
So the limit is, so I guess given that you're trying to keep in a high efficiency area,
Yes.
that efficiency limit caps the amount of thrust you can get per square meter, and that's what's limiting the amount of weight you can have in the structure and the amount of weight you can afford for control circuitry and for all the other components.
Well, I'm not. I have to think about it if I would use that word capped. I would think. I would say there's a curve.
Mm-hmm.
I mean, it's not wrong what you're saying. It's just.
But then I guess there's like how flexible how flexible are you with like that efficiency criteria?
So, right.
Yeah.
You have a graph. It looks like 30 watts per gram or 30 grams per watt of lift if you make it as light as it can possibly be. You know what I mean?
Mm-hmm.
And if you make it just a little bit heavier, you get like 10 grams per lift. And you add 1 more gram to it, and then it's like 2 grams, per watt.
Yeah.
So the efficiency curves are very sensitive. Like even the inverter, when I'm testing those on a bench in the other shop, if I put the wires too close to each other that go to the multimeter, the volt reading drops way down.
Mm-hmm.
Just because the wires aren't separated.
Yeah.
So I mean it's like sensitive to if you put your hand near it, voltage can drop.
Yeah. And then I guess part of your probably since you're going with the vertical takeoff, then you need to have that at least 1-to-1 thrust to weight ratio. Have you done any work trying to on fixed wings that you can get, because especially with glider wings you can get you need much less thrust per mass, especially you can launch from a catapult and then
it's inversely proportional to the glide ratio, right? Like if it's a really long glide ratio, you need hardly any power to keep it going, right?
Yeah.
But if it's a very efficient glider, like no power, you can just keep.
Yeah.
100. If it's 100 to 1 glide ratio, I think you only need 100th of the thrust, of the weight of it, of thrust to make it stay level.
Mm-hmm.
You know, but the thing is that this is actually, you know, when this thing flies on its side a little bit, the bottom sides of these, the sides of the collectors that are facing downwards flatten a little bit, and they're already teardrop shaped, right?
Yeah.
So they form perfect wing shapes.
So they become airfoils.
They're perfect, yeah. Well, perfect, yeah, a little bit. Reasonably nice airfoils.
Yeah.
Yeah. So what I did outside was I had this thing. I could, you know, pull up a video on the phone or something of it, but I had it hanging from a. When I put it on tethers that, on oh god, that was dumb. If I put it on, you know, tie downs like this, right? Mm-hmm. Then you can fly it like this high, and then if I make them longer, it's in no danger of like being destroyed. You know, so I keep them short, just so I can keep testing over and over and improving things. So, but if I put a tether above it, it goes way up high, a springy one, you know, then I can fly it way up high in the sky, and I can come down and it won't crash.
Yeah.
Right. So I had it on a tether above it, and the top of the tether above was on a slip ring, a little plastic ring that was on a tether going side horizontally. So when the thing took off, it would take off and then start going like this, sideways, and it flew about 15 feet or 20 feet sideways, flying, and you could see, and the tether up above it was kind of curved, like it was, you could see it wasn't supporting it, you know, for about 15 or 20 feet. So it's flown horizontally before.
Yeah. See, I've seen a video of some test plane that was like a biplane that suspended the electrodes from the wing spars.
Right.
That was
MIT's thing.
Yeah.
Yeah, they, you know, it's a dark story because they you know, said they're the first ever to lift a power supply with ion propulsion, and it's not correct. You know. But that said, anyway, you know, in the past, the thing is about that is it has a very powerful bungee cord for the, you know, elastic launching mechanism. It can produce, you know, kilograms of force, right, to force that glider up into the air.
Yeah.
And then it has a movable rudder and tail, you know, elevator surface. So it could go up and then come down and glide a long ways, and then you know, they could do that with the elevator, and make it level. So a glider that has this, you know, I forget the meters again. I like to think sometimes in,
Yeah.
empiric,
Yeah,
imperial, but it doesn't matter. Anyway, it has something like a 6-foot wingspan, a 16-foot wingspan, and weighs, I think 5 pounds, 2.5 kilograms. So a vehicle with a complete, streamlined wing surface that weighs 5 pounds and with a 16-foot wingspan should have a pretty good glide ratio, right? But they tested it with all those slats under it, and it didn't glide very far. It was more like 8 to 1, or not good. But as soon as they energize all those, they negate their own drag because they pull wind across themselves. So really, they should have tested the glide ratio without those, right?
Yeah.
So you've got the the glide ratio. It probably should have been tested without those, like I said, and
So it would imply that it's a much lower power than.
yeah, than they say. But if you calculate it, it's not a great. I mean, it's a very small percentage of what would be required to go straight up. And
So this is just a way to optimize a higher power version of it, which could then be used for a much heavier aircraft.
sure, if we were going horizontal, going vertical, going in vacuum.
So you just chose in vertical just because this is a very easy way to measure. You just measure power, and then the same methods could be used to get a fixed wing aircraft or something else.
Sure. I increased the efficiency of ion propulsion. Right?
Yeah.
I figured out a way to make ion
And it's just the
propulsion.
vehicle you're choosing.
Yeah.
Yeah.
Well, I mean, I grew up watching Star Trek.
Yeah.
Everybody says that's my age. And I thought, wow, that Star Trek shuttle's pretty cool. I thought, well, I don't know how to make a warp drive. I don't know if it's even possible. But I think that this ion powered propelled thing could carry its power supply someday. So I worked on it for many years until it did. And I just began to learn the physics of it. That's what it takes to make it happen. I started with big, heavy transformers. I started making them smaller and lighter, and until it got to this lightweight device. So I wish, there's so much more to show you, but I just don't know. You guys probably can't just do it all day. You probably have a lot of stuff to do.
Although we definitely,
If you have a few more minutes, I'll show you, but I'm not going to keep you.
I have a armory for the fencing team.
Oh, wow. Cool.
Got a much less exciting electronics, just like finding in the fencing team, like our wire, we have like wires for the electronic fence at scorekeepers, and those wires break all the time, so it's much of it.
That's interesting.
Yeah.
I have a few more minutes. I could.
Yeah, okay, sure. Anybody wants to